Okay, good morning everyone. Senan this side, and in this video we are going to solve this LeetCode daily problem, which is number comp. Although it's an easy problem, but you would still have to think a lot before actually jumping up to a solution. Because if you see, it's not exactly a complement. Basically, we are doing a complement, but not in terms of what computer sees, in terms of what as us human sees. We'll see what that exactly means. Basically, a complement of an integer is integer you get when you flip all the zeros to ones and ones to zeros. It's binary representation. For example, 5 is 101. In binary, it's 010. In complement is 010, which is basically integer 2. You have to return the complement. Now you see 5 and 1, you get the answer as 0, and the values of num is strictly greater than equal to 1. Okay, so first let us look at my notebook and let's see what are some complications that could arise. So yep, I'll see you in my notebook. Okay, so here we are in my notebook and we are given, let's say, 5, right? And the binary representation is 101. So what you want to do is take this, convert this to 0, take this, convert it to a 1, take this and convert it to a 0, and whatever is remaining, this is your answer, and this is basically 2. And basically you do not have to convert this to say that okay, this is 2, because this your computer will technically recognize this binary representation. Now what if you say, let's write 5 as 0101. Technically what you should do is flip this 0 as 1, as 0 as 1, but this is equal to, and that is not what you have to do. So by this you clearly get an idea. You need to find the last one in the representation, and from that and numbers, so the elements for that, because we have a 32-bit representation, right? Let's say we have 0 and 101, so the last one is this one, and what we have to do is find basically the complement of these individual elements. It would be 0, it would be 1, it would be 0, and you have to keep all of this as it 000. So 010 give you 2. So that is the point. Now first of all, let's go step by step to do. You see this, you're seeing 1 and you have to get an output as 0. You're seeing a 0, you have an output of 1. When you're seeing 1, you get an output as 0. So what you should understand is something known as bit manipulation, which is basically the thing that we are going to use is 1 XOR 1 to 0, 1 or 0 is to 1, 0 XOR 1 is equal to 1, 1 0 XOR 0. So this is the XOR operation. Basically what it does is, I want you to see is to observe this one, and say given a number 1, you XOR it with 1, you flip the bit. You're seeing a 0, you XOR it with 1, you see a 1, right? Now let's look at a sample test case. Let's say for 13. 13 is what? 13 is 1101 in binary. Fine, this is in binary. What should the answer be? You take all the bits and flip them, right? So the answer would be 0010, which is again your answer as what you got in, not here, but this is again 5 is also giving you 2 as an answer. 13 is giving you a 2, giving you 2 as an answer. So yeah, the question is not exactly as straightforward as you think it would be, because this 13 and 5 are having the basically same complement. So first of all, this complement operation is not invertible. From 5 you could go to 2, from 13 you could to 2, but when you try to go from 2 back to 5 or 13, you cannot do that. It's not a unique representation of complement. So let's say, since we are using 32 bits, assume we have some number of zeros, and let's take an example, 5 again, 101, and let's say what I do is I write this number, right? And I write 1 1 and 1. Basically I am counting the number of bits in this 5, but the last bit is I am finding that number 1. I'm basically placing all the ones before that position. Now what you can do is basically perform an XOR operation. If you see above, 0 XOR 0 is 0. So if you have the same bits, the answer is 0. If you have alternating bits, opposite bits, you have 1, same bits, answer is 0, and bits, answer is 1. So that is the ability of the XOR operation. So let's just do this. 1 XOR 1, 0 XOR 1 is 1, 1 XOR 1 is 0, and 0 XOR 0 is 0, so all the elements would be 0, would be your number. So now our task, given a number, like this. In the binary representation, you need to generate a number like this and perform an XOR operation between these two elements, right? So first of all, I need to have a count of how many bits are there. Basically, all the number of bits starting from right till the last significant bit. Okay, let's see how do we actually implement this in our code. So here we are in our on our laptop. What I do is I basically make a copy of num, right? Because I'm just changing the n later on. I just don't want to do it with this. So I take a copy of num, I take an answer as 0, I take a count. So what I do is I count the elements which are, so till the time n is not 0, what I do is I increase the counter and I shift n by 1. So this shifting operation again. So let's say we have a number 101 and you do it by 1 by 1. So what you find is you take all the elements, shift one position to the right and you disregard the last. So would be again, if you would shift again by 1, this would be what? 1, disregard the last element, whatever the remaining element is your answer. Again, if you by 1, nothing is there to do, so what you do, your answer would be 0, because all of these elements would be having the remaining zeros. 0 zeros are listed till the time my number is not 0. Since if you observe, right shift one time, we did right shift second time, we did a right shift third time to get the value 0. And how many ones did we want in this case? It's again exactly equal to the count that we are doing. So you get this point. Now given this count is greater than 0, I am just adding 1 into the end, right? And I am doing a counter minus minus, and if at some point counter is equal to 0, I don't shift my answer to a step left. Or a better way to do this is do a count, or let's leave it like this for simplicity. Okay, so basically you could write a one line function to do this, but this is more clear and more understandable. And now what you do is you take the XOR of these two numbers in the end, like we did in our notebook. So we did final XOR, right? Is basically our answer. This is what is stored in our answer variable, and this is stored in our num. Finally, we take an XOR and we return the final answer. Yep. So what is the basically the time and space complexity of this solution? So if you think it closely enough, the possibly say the time complexity and space complexity constant. Hear me carefully, right? Because at max we know this while loop would go to 32 iteration, so that is a constant, right? At max, because this integer is stored in a 32-bit representation. So if that is the case, this while loop and this while loop can at max go to 32 iteration. So at max we know regardless of the value of num, we could have 64 iterations of this in that way, but a big but. So before that, this is a constant time operation. The thing that we are doing in this is a constant time operation, this as well. The while loop could you could consider basically it is a constant, but it's not. So let's look at what is the exact solution. So if you look at 101, which is 5, right? So how many iterations did it take in the while loop for calculating the number of the most significant one? So what do you think it would be? So if you look closely, if you do a log operation, log of base 2 of 5, what is this? It's near about somewhere between 2 to 3, somewhere in between. I think that is correct. And what is log base 2 13? Somewhere between 2 to the power 3 is 8, 2 to the power 4 is what, 16. So somewhere between 3 and 4, right? Or let's take the seal value of this. So in this case we would get the value as 3, this we would get value as 4. Let's look at one more example. So log base 2 and let's say 64, and the seal of the 64 has how many bits? So 0 0 zeros. Okay, let us write it like this. This is 1, this is 2 in binary, this is 4 in binary, 8 in binary, 16 in binary, this is 32 in binary, and this would be 64 in binary. I assume I'm not wrong. And how many we having is 1 2 3 4 7, and 2 to the power 6 is what? 2 to the power 5 is 2 to the power 6 to 64. So log base 2 of 64, basically 6. You would take about 6 iteration in the while loop, because or let's say you can just add +1 to it if you want. You seeing you are calculating 3 4 5 6 and 7. basically your count value would be 7 after. So somewhere about this, you could just do this plus 1 and take the seal. Basically this is of the order of log n. So whenever you are doing this, your number of iterations this while loop will go is log of n. It won't go to 32. And yep, more or less this is the answer that I'm trying to present. Time complexity would be log n, looking at the example that we just gave, right? So we would basically calculate the number of bits using log n, and you could definitely do this without a while loop and directly use a log function to figure out the number of bits. Then you can do some shifting left and right and finally return the XOR. Basically you could do all this in a couple of lines, 2 or 3 lines at max. This is more clear to understand. That's what I'm trying to do. And yep, that was the video. Hope I was able to explain this to you. And yep, thanks for watching, and I'll see you in the next video.